Okay, so hello, I'm Kripa from DFKI Germany, and I'll be presenting this paper on 3D shape processing by convolutional denoising autoencoder on local patches. So in the beginning, I'll start with some motivation. So before the application of any CNN on 3D shapes, we need to have a common shape parameterization on which it is defined. So the most famous or the most simplest one is the voxel grid parameterization, which gives a very crude global shape outline. But our main focus here is to find it on local shapes, local patches to capture high surface details. So these global outline based descriptor like voxel grid provides quite good representation for the task of classification and global shape generation. But for local fine scale details, it's not very valid. So with this, I come to my contribution. So we apply convolutional neural network on fine scale surface details on local patches. We get these patches from in this contribution presented in this slide, which produces patches of high in amount, which covers all the surface variations, and also it has sufficient in amount to train a deep neural network. So this is the overview pipeline. We generate patches on 3D meshes using the pipeline in the last slide, and we train a CNN on that clean patches. Then at the test time, we get a noisy mesh with holes, and we use that CNN trained to denoise it. So this is the rough CNN architecture. It consists of the simple encoder and decoder modules. It takes a 2D patch with missing information, passes through some convolution layers with optional fully connected layers in the middle, then followed by a series of transpose convolution. We also use some skip connections, which is motivated by 2D inpainting networks. This is the CNN architecture in details. So the network complexity increases as we go from left to right. In the end, in the rightmost network, we use the longest network with 12 layers with skip correction. And this is some of the qualitative result, which shows the reconstructed patches with the missing information. So as you see, the quality increase when you move down to the higher network with skip connections. We found that our network very accurately captures the details when the missing information is quite low, but even when the missing information is quite large, as you see on the right part of the patches of this table, the longer network still able to generalize it well. So this is the final reconstruction result of the meshes, and we compare this with two simple methods. One method is the hole filling method of MeshLab, and the other method uses something similar to us, but instead of learning deep neural network, they use linear dictionary model. So qualitatively, our result looks better than them. So this is some quantitative result. It shows the also there is a small plot in the right. It shows the importance of skip connection. So you see, as we increase the network parameters, the error decreases but kind of saturates in the end. As we move further, then the error slightly increases and it goes really down with the introduction of skip connections. For more details, you guys are welcome to visit me in the poster. Thank you.